Hi and welcome back. In this video I'm going to tell you about quantum dynamics, and as in previous videos I will be comparing dynamics of classical systems with dynamics of quantum systems. In classical case one can describe dynamics of a probability vector by so-called transition matrix. Transition matrix is essentially a probability to have a transition from a state number j to state number I. We usually represent a transition matrix as a directed graph with weighted edges, and each weight of an edge shows probability to have a transition from one node to another. In quantum case we have a similar situation, but instead of transition matrix we have a fourth rank complex tensor which is called quantum channel, and this tensor has specific property that are called complete positivity property and trace preserving property. One can read more about quantum channels and their properties in a book by Alexander Semyonovich Holev. Like in a classical case, in quantum case, quantum channel induces transformation of an input density matrix to an output density matrix. In classical case, transition matrix induces so-called Markovian process that shows you how initial probability vector evolves in time. In quantum case we have a similar situation, and quantum channel induces so-called quantum discrete Markovian process that shows you how an initial density matrix evolves in time. Now let us play with code and consider an illustrative example of the polarizing channel with unitary rotation. The dynamics of a density matrix under the action of this channel is represented on a slide, and one can code these dynamics up by using TensorFlow and calculate dynamics of a qubit and direction of this channel for 100 time steps. Now let us have a look on the right hand side of a slide. One can see that dynamics start from a pure state and then rapidly goes to the center of block ball. The central point of a block ball is a density matrix, is a state with maximal uncertainty, with maximal von Neumann entropy. Any quantum channel phi can be represented by a so-called Cherry matrix. Cherry matrix is a matrix of size n squared by n squared, which is a complex and has specific properties. First property is that partial trace of Cherry matrix should be equal to the identity matrix. And second property is that Cherry matrix should be a positive semi-definite matrix. One can imagine set of all Cherry matrices as a subset of a cone of positive semi-definite matrices. One can also represent set of all Cherry matrices as quotient manifold that allows us to integrate this set of all Cherry matrices to the framework of Riemannian optimization. Now let us consider the case of deterministic transition in classical and quantum cases. Deterministic transition is a kind of transition that doesn't introduce any uncertainty into a system. In classical case, deterministic transition can be described by a so-called permutation matrix, which is a special case of transition matrix. One can show that that dynamics induced by permutation matrix doesn't increase Shannon entropy, which means that this type of transition doesn't introduce any uncertainty into a system. In quantum case we have a similar kind of transition that is called unitary transformation, and a quantum channel that leads to this type of transition is represented on the right part of a slide. One can also show that this kind of transition, which is called unitary transition, doesn't increase von Neumann entropy, and it means that this kind of transition doesn't introduce any uncertainty into a system. Now let us consider a geometrical interpretation of a deterministic evolution of pure states. In classical case, one can imagine deterministic evolution of pure states as a transition from one vertex of a probability simplex to another vertex of a probability simplex. In quantum case, a situation is a little bit different. deterministic or unitary evolution of pure state in quantum case can be imagined as transition within surface of a set of all density matrices. One can also describe unitary evolution of pure states in terms of psi vectors or state vectors. And equation that describes this transition of psi vectors is called discrete Schrödinger equation, and it is shown on the right hand side of a slide. So now let us again play with code and let us consider unitary evolution of a qubit. We can code this evolution up and calculate as before dynamics of a qubit for 100 time steps. Let us have a look on the right hand side of a slide. One can see that state of a qubit remains on a surface of a Bloch ball. That means that purity of states is preserved. And it is well agreed with general geometrical interpretation of a unitary evolution of a pure states that state remains on a surface of on a boundary of all density matrices. Unitary matrices that describes transition, deterministic transition in quantum case are very important in quantum technology. And fortunately, unitary matrices form a smooth manifold that is special case of so-called the complex Stiefel manifold. That's it about quantum dynamics, and thank you for your attention.